So, to summarize what we have been talking so far, we started with a differential equation of this form 1 minus x square y double prime minus 2 x y prime plus alpha alpha plus 1 y equal to 0. And in the power series method, we used a trial function of the form y is equal to sum over n equal to 0 to infinity c n x raised to n. And when you substitute this in this differential equation, then you get a relation between Cn plus 2 and Cn. We call this the recursion relation. And this can be written in this form. Okay. So, you can and what we saw is that all the odd terms are proportional to C1 and all the even terms are proportional to C0. So, we can write our solution y as C0 sum of even terms, and even terms are polynomials of the form x raised to 0, x square, etc., x4. So, this is a polynomial containing only even terms, even powers of x. This is a polynomial containing only odd powers of x, like x, x cube, x5 and so on. Okay. So, it will have C1x, C3x cube. Okay, C3x cube is C3 is proportional to C1. So, there is a constant of proportionality times C1 and so on. Okay. We can just to formally you can show that you can write Cn is equal to, if you have an even polynomial, if you have an even coefficient, so C2n, okay, this is proportional to C0. So, this is C0 multiplied by something, and that something is minus 1 raised to n. Okay, so, each time you go one lower, you get a minus 1. Alpha minus 2, what you have is alpha minus 2, alpha minus 4, all the way up to plus 2, and then you have, so this whole thing multiplied by alpha plus 1, alpha plus 3, this goes to alpha plus 2n minus 1. This whole thing divided by 2n factorial. Okay. So, essentially when you write Cn plus 2 in terms of Cn, you have an n plus 1, n plus 2. Then when you write Cn in terms of Cn minus 2, you'll have a n and n minus 1 and so on. And so when you keep doing this all the way to C0, then you will get 2n factorial. So, this is valid for even, so all even coefficients can be expressed in terms of C0, and similarly all the odd coefficients can be written in terms of C1, and this is minus 1 raised to n, alpha minus 1, alpha minus 3, alpha minus 2n plus 1. Okay. Then alpha plus 2, alpha plus 4, n divided by 2n plus 1 factorial. Okay. So, suppose you want to find the coefficient of x raised to 10, that will be C10. So, C10 means you put n equal to 5. Okay. So, you put n equal to 5, you can find the coefficient of C10. So we can write C10. Okay. So, if I put n equal to 5 here, then I have equal to C0 minus 1 raised to 5, and then what I will have is alpha minus 2, minus 4, alpha minus 6, alpha minus 8. So, it goes all the way to alpha minus 2n. Alpha minus 2n is 10 plus 2. So, it goes all the way to alpha minus 8, and then you have plus 3 7 alpha plus 9. So, all the way to alpha plus 2n is alpha plus 10, 10 minus 1 is 9. So, it goes all the way to alpha plus 9. This whole thing divided by 2n factorial, that is 10 factorial. Okay. So, C10 can be expressed in terms of C0. Notice that all this is just a constant, it just depends on alpha. Okay. So, it is some constant that depends on alpha times C0. Similarly, if I want to write C7, I can write it in terms of C1. Now, when so if you want to calculate C7, then n has to be equal to 3. So, 2n plus 1 is 7, and if n equal to 3, then you have C1 minus 1 cube alpha minus 1 alpha minus 3. Now, 2n plus minus 2n is n is 3. So, alpha minus 3 alpha minus 6 plus 1. So, it goes up to alpha minus 5. So, that is the last term. And then you have alpha plus 2 alpha 4 and alpha plus 2n. So, alpha plus 2n is alpha plus 6. So, the last term is alpha plus 6. So, that is all you divided by 7 factorial. Okay. So, we can write both even and odd coefficients in this form, in the form of this power series. In this power series method, we can write even coefficients as proportional to C0 and the odd coefficients proportional to C1. Okay. And notice that whenever you have a coefficient, always the corresponding factorial appears in the denominator, and then what you have in the numerator are various terms like alpha minus something and terms that look like alpha plus something. So, if alpha minus odd numbers, alpha plus even numbers. So, there is always this kind of symmetry in this relation. Okay. So, the Legendre, this equation, it appears very naturally in the solution of the wave equation in in spherical coordinates, and this appears to in the solution of the angular part of the wave equation. And so in the quantum mechanics courses, it appears when you are solving for the angular parts of the wave function for any spherically symmetric system. So, for example, if you are solving for the hydrogen atom, okay, and you are solving for the angular part of the wave function, then the Legendre polynomials appear and Legendre differential equation appears. So, typically when this appears, your x, the argument x is actually cos of theta. So, in the spherical, so what you call x in the differential equation is in physical applications. So, okay, what appears is cos theta, and what you have is a differential equation where the argument is cos theta. Okay, so you have the wave function is a function of cos theta, okay, and all these derivatives are with respect to cos theta. Okay, so this leads to the spherical harmonics. Which are related to the angular part of the wave function. So, the angular part of the wave function of wave function. Okay. So, now one of the things that you have to think about whenever you have a series like this, whenever you have a power series of this form, okay, the immediate question that you should ask is this does this series converge or does it diverge? So, what you mean is that this series, as x becomes very large, does it goes to plus or minus infinity or does it go to some finite number? Okay. So, that is a question that that you immediately should ask whenever you see a power series. Okay. Now, in these kind of as I said, in physical applications, okay, in the spherical harmonics, x corresponds to cos of theta, okay, and so the argument x varies between -1 and +1. So, cos theta is between plus and -1. Okay. So, what this implies is -1 less than equal to x less than equal to 1. Okay. And if x goes between -1 and +1, okay, if x goes between -1 and +1, now so long as x is less than 1, okay, so long as x is strictly less than 1, x is strictly less than 1, or rather or it is strictly greater than -1, okay, then this series will converge. Okay. So, this power series, if x is less than 1, okay, if absolute value of x is less than 1, so this converges for, it always converges. So, whatever power series you take, it will always converge if absolute value of x is less than 1. Okay. So, the only concern is what happens when x equal to 1. Okay. Now, if you look at these terms, okay, so you have to consider what happens to these coefficients. Okay. When x equal to 1, you just have y equal to sum over n equal to 0 to infinity C n, and so you have to look at this series of coefficients and you have to decide whether they converge or they diverge. So, the point is, this series, it converges for x is for absolute value of x less than 1. Okay. Now, when x is equal to 1, when x equal to 1, then this series becomes sum over n equal to 0 to infinity C n, and C n, since I mean it has infinitely many terms, and depending on the value of alpha, these terms either there are infinite terms or there are finite number of terms. Okay. So, suppose alpha is an integer r. Okay. So, suppose alpha is an integer r, okay, and I will just choose a positive integer, r. Okay. So, what that would imply is that C of r, okay. Now, if r is even, okay, C of r can be written in this form. Okay. So, C of then instead of n, I put r by 2. Okay, I can write this form. Okay. So, C of r can be written as C0 r by 2 all the way up to alpha minus 2n plus 2 or r plus 2. Okay. And what we have said is that alpha is equal to r. Okay. So, now if alpha equal to r, then I replace all the alphas by r, and what I get is r minus 2 all the way to r minus r plus 2. Okay. And then you have r plus 1, r plus 3, r plus 2n is same as r minus 1. Okay. So, you notice divided by r factorial. Okay. So, so it goes from r minus 2 all the way up to 2. Okay. So, basically this series looks like 2, 4, 6 all the way up to r. Okay. R is an even number. So, it is a product of all even numbers smaller than r. Okay. And this goes from 1. So, this is 1, 3, 5 all the way up to r plus 1. Okay. So, this is a product of all odd numbers. Okay. Okay. So that is what you get if you do this. Now, what about C r plus 2? Okay. What about C r plus 2? Now, if you had r plus 2, then this would be C 0 minus 1 raised to r plus 2 is r plus 2 by 2 is r by 2 plus 1, and here you have r plus 2 r minus 2 all the way to r plus 2 . So, sorry, you have alpha is equal to r. So, you have r minus 2 all the way up to r minus, now 2n is r is 2 into r by 2 plus 1. So, that is 2n. So, 2n is r plus 2. So, minus r minus 2 plus 2. Okay. So, where I had 2n, I put r plus 2. Okay. So this term alpha minus 2n plus 1. So that is alpha minus r plus 2. So that is alpha is r minus r plus 2. Okay. So just to make it explicit, I put it this way, and I had a plus 2 or plus 1. Or sorry, r. So you have, oh no, sorry, oh no, plus 2, this is 2, r plus 2 plus 2. Okay. Okay. So what you have here is alpha minus 2n plus 2. So you have alpha minus 2, alpha minus 4, alpha minus 6, alpha minus 8. It keeps going on all the way to alpha minus 2n plus 2. Okay. So this is alpha minus 2, then alpha minus 4, alpha minus 6, all the way to alpha minus this is 2n, alpha minus 2n. 2n is same as r plus 2. So alpha minus r plus 2 plus 2, and then you have all the other terms like alpha plus 1, or alpha plus 1 is r plus 1. Up to r plus 2 plus minus 1. Okay. This whole thing divided by r plus 2 factorial. Right. So notice that the C r plus 2 term has this term. So this is r plus 2 minus r plus 2. So this term goes to 0. So that implies C r plus 2 equal to 0. Okay. So this is the result that you see. If alpha is a positive integer r and r is even, then C of r plus 2 is 0. Okay, and this immediately implies C r plus 4 is proportional to C r plus 2 equal to 0. Okay, C r plus 4 is just a multiple of C r plus 2, and that is also equal to 0, and so implies C of any C of x equal to 0 if x is an even integer and x greater than r. Okay. So that means all the even terms for which are greater than r are all 0. Okay. This implies even terms only up to r. Okay. So the sum of even terms that goes only up to r. Okay. So this is an important important property that that if alpha is an integer, if alpha is a positive, if alpha is an even integer, then then the even series truncates at alpha equal to r. Okay. Now, if alpha is an odd integer, if r is odd, okay, then you can show that, then it is easy to show, you can go by the same arguments. If r is an odd integer, then when you take c of r plus 2, okay, which will be another odd integer, that will be equal to 0. Odd 0, all odd terms for Cx with x odd and x greater than r are 0. Okay. So essentially, if r is an odd integer, then also all the odd terms that are where the power of x is greater than r are 0, and if alpha is an even integer, then all the even terms with power greater than r are 0. So what this means is that if you choose alpha to be an integer, okay, so if alpha is an integer r, then your series truncates at r, okay, then one of the two series truncates at r. Okay. So now we come back to our solution. We know that if alpha is an integer, then depending on if it is even, then the even series truncates at r. If it is an odd integer, then the odd series truncates at r. Okay. And this is what is used in order to motivate solutions of this Legendre equation in real physical problems. So now we had y is equal to C0 sum of even terms plus C1 sum of odd terms. Okay. And so if r is an integer, then one of these series terminates at one point. Okay. So one of these series will terminate if r is an integer. Okay. Now how do we use this fact when we are applying it to real physical problems? So suppose you are applying it to spherical harmonics, then one of the things you will say is that your y is actually corresponds to a wave function, and the boundaries at x equal to plus minus 1, y should be finite. Okay. Now suppose this series does not truncate. Okay. So suppose you had an infinite series, okay, of coefficients, then you can show that that is a divergent series. Okay. So implies series should be finite. Okay. So this is in the particular case of this Legendre polynomial of this differential equation where we had a particular recursion relation. Okay. So you can have convergent series, but the series that we considered, that turns out to be divergent if at x equal to 1. Okay. So that implies, so if alpha is an integer, y is equal to, and let's say let's choose even for now. So then y equal to C0 times a polynomial of degree alpha. Okay. So this is a polynomial of degree alpha. That means it has terms it has terms like 1 x square, x4 all the way up to x raised to alpha. Okay, alpha is an even integer. Okay, and then you have C1 times, this is a series, this is an infinite series of odd terms. Okay, so so this is an infinite series of odd terms, and what we will demand is that C1 equal to 0. So, if C1 equal to 0, okay, so we choose C1 equal to 0, okay, and then that will ensure that that your y is finite at the boundaries. So, y of plus minus 1 is finite. Okay. So, if you did not have C1 equal to 0, if C1 was not equal to 0, then you would have an infinite series of odd terms, and when x equal to 1, this series will go to plus or minus infinity. Okay. So, therefore, you force C1 equal to 0, so that you only have this, okay, and so y is equal to C0 times polynomial of degree alpha. Okay. And this polynomial of degree alpha is called the Legendre polynomial. Okay. So, it is a polynomial, it is a function of x. So, it is a function of x. So, it is denoted by p alpha of x. So, it is a function of x, okay, and it is a polynomial function, it is denoted by p alpha. Alpha is because it is a polynomial of degree alpha. Okay. You can similarly you can do this for odd also. So, if alpha is odd, y, so you demand C0 equal to 0. So, y is equal to C1 times polynomial of degree alpha. Okay, and this is also Legendre polynomial. Okay, so the Legendre polynomial is a polynomial function, is a polynomial function, and it has degree alpha. Okay, and so it is given this name because it appears quite often. Okay, now we can write the first few Legendre polynomials. So p0 of x, this is chosen to be 1. Okay, so p0 of x is 1, p1 of x, okay, this is x. Okay, so remember we had an arbitrary choice for C0 and C1, okay, and p0 means a polynomial just of degree 0, so that is just a constant, okay, and that constant is chosen to be 1. Similarly, p1 is also chosen to be 1, okay, and this gives you p2. Okay, so you can work out p2 once you know p0, you can work out p2. In fact, you can use the recursion relation to write. You can go back to the recursion relation and you can write that p2 is minus 1 into p0. The coefficient of 0th polynomial. Okay, so I think you would be a little more careful. So, p2 of x is equal to C0 plus C or so 1 plus C2 by C0 x square. Okay. So what I did is I wrote y is C0 times a polynomial of degree alpha. Okay. Now, if this polynomial truncates at 2, since alpha equal to 2, this polynomial will end at 2. So, P2 looks of this form. Okay. And so what you need is C2 by C0, and so this works out to 1 minus, so this works out to half 3x square minus 1. Okay. So you can work this out and show that this is indeed the case for this. Okay. So what we have seen is that you can construct each of the polynomials one by one, and you can take this series further on. So there are many interesting properties that you can derive. These are just based on the recursion relation, and I just want to remind you the recursion relation was a relation that related Cn plus 2 equal to Cn times something. Okay. And that something was minus Cn times alpha plus 1 minus n plus 1 divided by n plus 1 n plus 2. Okay. So this was the recursion relation. So you could calculate C2 by C0 using this relation. Okay. So C2 by C0 means n equal to 0. N equal to 0, you have alpha plus 1 divided by 2. Okay. And if you had alpha equal to 2, then you just have 2 into 3 by 2, that is 3. So that is where you get this from. Okay. So so you can use this. So starting with this recursion relation, you can calculate all the polynomials. Okay. So what we said is that P2 of x is actually proportional to this. Okay. So there is an arbitrary constant of proportionality that you can add. So it is proportional to 1 plus C2 by C0 x square. So and then P2 is actually equal to half 3x square minus 1. Okay. Now or I can write this as minus half 1 minus 3x square. Okay. So now I said that this constant before this 1 is arbitrary. Okay. So this constant is chosen arbitrarily. In fact there are some ways that we will talk about later how you choose these constants, but essentially what you have is 1 minus 3x square. Okay. Now the 1 we got from the 1 corresponds to the leading term in this polynomial series. The second term is C2 by C0. Okay. So this C2 by C0. Okay. Now this C2 by C0, you can calculate C2 by C0. If you want to calculate C2 by C0, you use the recursion relation. So Cn plus 2 is related to C0 in to Cn in this way. Now you put n equal to 0, then you have C2 equal to C0 times something. Okay, n equal to 0. So this term will go away. Now when alpha equal to 2, okay, so since we are calculating P2, you need to put alpha equal to 2. So you put alpha equal to 2, okay, then C2 by C0 becomes minus 3, okay, and that is this minus 3 here. Okay. So except for this constant of proportionality, okay, you know how to get the Legendre polynomials. So except for this constant of proportionality, you can derive the Legendre polynomials using this method. Okay. Now this pretty much is the entire way of how to use the power series method, and it is a very powerful method. It can be used for many different kinds of problems, and what I have illustrated here is the basics of the technique. So you start by assuming a trial function of this form, and then you get various recursion relations, and actually starting from this recursion relation you can derive all the polynomials individually. Okay. Remember that we had to impose the condition that if alpha is an integer, then the series truncates at some value, and that allowed us to set one of the coefficients to 0, and that is what gave us these Legendre polynomials. So, these polynomials are quite since they appear in the solutions of these equations, they are given a name. Okay, and these equations are quite important in various applications. Okay. Now, there are some interesting properties of these polynomials. So, when you take polynomials of different degrees like P0, P2, P3, P4 and so on, they satisfy some interesting relations. So, one of them is also called a recursion relation. Recursion relation for Legendre okay, and this is something that you should try to work out as a homework. You can try to work out. Okay, I will give you the relation n plus 1 to n plus 1 x p n and this plus n p n minus 1 x. Okay, so this is something that you can derive. You can derive these based on these expressions for the polynomials. It's not that straightforward to derive, but we'll just assume that it's possible to derive these. Okay. Notice now this is a very interesting relation because it relates p n plus 1 to p n and p n minus 1. Okay. So if you have a polynomial, or in other words, it relates p n to p n minus 1 and p n plus 1. Okay. So if you have x times p n, then it is a linear combination of p n minus 1 and p n plus 1. So I'll write this in a slightly different way. So x times p n of x is equal to n divided by 2n plus 1 p n minus 1 of x, okay, plus n plus 1 divided by 2n plus 1 p n plus 1 of x. Okay. So, x times p n is a linear combination of p n minus 1 and p n plus 1. Okay. So this is a very interesting relation. Okay. And it turns out that this one relation is turns out to be very important when we are deriving selection rules in spectroscopic transitions. Okay. So, we will come back and we will see this relation at that point too, or similar relations involving other polynomials. Okay. The other there are some more interesting properties of these Legendre polynomials. I will just summarize 3 of them, and then before we go to the next part of this power series solution. The 3 of them, first is what is called the Rodrigues formula. And this is also something that so this is a formula that gives your p n. So, by 2 raised to n factorial one minus x square raised to n, sorry, 1 minus x square. Okay. So, the point is that if you want to derive any polynomial, and by polynomial I mean the entire polynomial, not just the individual coefficients, the entire polynomial, you can derive it starting with so suppose you want to write you want to find the value of p4. Okay. So, then you just put n equal to 4. So, you take 1 minus x square raised to 4, you take the 4th derivative of that, okay, and then you multiply it by minus 1 raised to 4 divided by 2 raised to 4 factorial, and what you get will turn out to be the Legendre polynomial. So, this was a formula that was derived by Rodrigues. You can verify it for n equal to 2, 3. Okay, so that's another exercise for you to do. Another interesting property of the Legendre polynomials is a property of a generating function. Okay. And what you can show is that this function 1 over 1 plus 2 x t 1 minus 2 x t plus t square raised to half. So if you take this function, okay, and you write this as a Taylor expansion in t. Okay, so if you write this as a Taylor expansion in t, okay, so it looks like 1 plus some constant into t plus some constant into t square plus, okay. So here I am treating this as a function of t, okay, and this constant is a function of x, okay, and what appears will be exactly the Legendre polynomials. Okay. So if you write this as a Taylor series in t, okay, then what appears in this Taylor series will be the Legendre polynomials, and this is a direct consequence of this Rodrigues formula. Okay, so you can look at Rodrigues formula and you can show that this is indeed a generating function. Okay, and interestingly, p0 of x is just 1, so you can multiply this by p0. Okay, so all the polynomials can be generated from this simple looking function. Okay. Lastly, we will mention one property of Legendre polynomials that can be proved, okay, and this property is the orthogonality. Orthogonality of so this is integral minus 1 to 1 p n of x p m of x delta n. Okay, so that means so this is equal to 0 if n is not equal to m, equal to 1 if n equal to m. Okay, so there are two things in this. First of all, if you take n and m to be different from each other, okay, then the integral will be 0, will be identically 0. Okay, and in order to show this, you can use this relation, okay, and or you can use you can consider the case where so clearly, so if n not equal to m and n is odd and m even, or vice versa. So if one of them is odd, one of them is even, okay, then you have an odd function multiplying an even function, their product is an odd function, then clearly this is equal to 0, then integral is 0, equal to 0. So if one of them is odd, one of them is even, obviously it is 0, but even if they are two even functions, even if both these are even functions, but n is not equal to m, it turns out to be 0. So suppose I take p2 times p4, okay, dx from minus 1 to 1, this turns out to be equal to 0. Okay. Obviously, if I had taken p3 and p4, you would have said that p3 contains only odd terms, so it is an odd function of x, P4 contains only even terms. So, it is an even function of x, their product is 0, but even if you take any two different functions that are both even. So, this is also even, this is also even, the whole integrand is an even function. Still this when you take two different polynomials, their integral is 0, and to show that you can use such a relation. Okay, you can use a relation like this. So you can write you can write one of these as in terms of p n minus 1 and p n plus 1. Okay, and clearly integral of integral over whenever. So and each of those integrated with this will give you 0. Okay. So, in other words I can write this as, I can write P2 as some as P3 divided by x plus P5 by x, okay, some constant times P3 by x and P5 by x. Okay. And clearly when you do these integrals, they'll individually go to 0. Okay. So the point is that when you take any two different polynomials, any two different indices, then it goes to 0. This integral goes to 0. Now, if you choose n is equal to m, then you just get p n square dx. Okay. And this is where our choice of the constant multiplying p n comes into play. So we choose our constant such that p n square dx equal to 1. Okay. This integral from minus 1 to 1 is 1. Okay. So this is as much as I want to say about Legendre polynomials. Okay. And in the next class we will start looking at another power series method called the Frobenius method. Okay. So it turns out that this normal power series methods works in some cases it is not so useful, and we have to do something called a Frobenius method. So we'll take that up in the next class.